Okay, let's start our lecture number 15. And today we start the subject of magnetostatics. And the summary of today's class is this one. You can see we're going to talk about the original experimental law that defines the magnetic effects, the law of magnetic force between circuit elements, and then the Biot-Savart law that is useful for determining magnetic fields of current distributions. Then we are going to talk about the intermediate quantity that is employed to determine the magnetic field, which is the magnetic vector potential. It has the same role in magnetostatics as the scalar potential has in electrostatics, so we are going to talk about it. And we will today conclude with Maxwell's equations for vacuum magnetostatics. We are still not going to use material media in this formulation. We are going to introduce in the next lecture. References for this lecture: Jackson chapter 5 and our ebook chapter 5. The interesting thing about magnetostatics is that until, let's say, the 18th century, magnetism was associated with magnetic materials, but in the early 70s, sailors in ships started to notice that every time there was a natural discharge in the atmosphere, the kitchen utensils became magnetized, like pans, forks, and knives. And in 1750, Benjamin Franklin started to understand the electric nature of natural discharges, and he conjectured that because of those effects on the magnetization of metallic things on ships, he started to conjecture that there would be a connection between, between electric currents, which he was understanding that natural discharges were due to electric or equivalent to a very high electric current. So it started to establish a connection between electric current and magnetism. He couldn't pursue his ideas because there was no, in lab, he could not do experiments in lab because there was no power supply for doing experiments to generating currents until late 70s, 1700s, when Alessandro Volta developed the pile battery. Then scientists started to make experiments in laboratory so they could circulate currents. And one of those scientists was Ørsted. In 1820, he showed that an electric current on a circuit, he had a Alessandro Volta battery and a loop, a circuit, a straight wire. It could produce a current, and he observed that the compass needle would deflect under certain conditions nearby a straight wire. So we have this. I'm going to describe briefly, qualitatively, what was the experiment, and then a number of scientists like Biot-Savart, Ampere, they developed the mathematical modeling that would establish the connection between a magnetic effect, a field, and circulating electric current. Okay. In terms of our formulation, so just to there was some. We know today that the magnetic fields are generated by currents. Magnetized material we are going to see in our next lecture. A magnetized material is a collection of microcircuits, atomic microcircuits, which involve the electric charge that has some state of motion, and that produces a current, and every motion, every current will produce a magnetic field. So the natural magnetization of matter and the magnetic fields produced by circulating currents are the same effects. So so some things that we know, there's no magnetic monopoles, differently from the electric effects. We have magnetic electric monopoles, the point charges, for instance, but we don't have that in magnetism. And magnetostatics is defined as the set of laws under the stationary current regime. In other words, by stationary means that the divergent of J, the current density, is 0. So it means that magnetostatics is the set of rules of mathematical phenomena in which J is solenoidal. So J forms closed loops of currents. Okay. The magnetic effect is naturally observed visually, can be observed. If you use for instance, a magnet, right? And iron fillings, you spread iron fillings around the magnet, put them on a table, you can see the magnetic field lies naturally. And in fact, that's how people define the magnetic field vector, just by looking at those iron fillings, you know. So for like this one, you can see naturally the field lines are those in which the magnetic fillings align. And also, you can see that the magnetic field that is observed experimentally is that, I mean, if we put a compass nearby, the needle is going to align along the magnetic field. So naturally, a magnetic effect was defined as that of a type of vector in which if you have a compass, you can determine this vector, at least the direction of this vector, by looking at the direction of alignment of the magnetic needle. So the magnetic field has a nature that can be at least qualitatively visualized. So what Ørsted observed when he had a straight wire in a magnetic needle was something like shown in this diagram here, in this picture. So in fact, he was trying to demonstrate a heating effect due to a current carrying wire. But he had a compass. He also wants to demonstrate that, I think, right? So he had a compass nearby, and he tried to see if there would be any deflection on the compass. Okay. So when he aligned the compass on a plane like so, a plane that cuts the wire at 90 degrees. In other words, have a plane, have a wire, put the compass like this. Then he would notice every time a deflection at right angles relative to the wire. So the wire is like this, the needle would come like this. We have obviously the magnetic field of the Earth, depending on on how high the field strength was for the current carrying wire, you could have perfect 90 degrees, or you could have a small deflection, right? But the tendency was the needle to follow, to go through 90 degrees relative to the wire. I mean, if you put it even closer, then it's really going to go at 90 degrees. So, for instance, when they put the needle like this and the wire like that, the needle like this, so there would be no, I mean, the needle would try to go against the wall of the compass. It wouldn't deflect. So if you put the compass on a plane that's 90 degrees with the wire, then it would have a deflection always at 90 degrees like this. This is a top view. Have a current going up on the plane of the paper here. Okay, so the needle is always going to go at 90 degrees relative to the wire. So this was the first real evidence. I mean, there was prior evidence, as I mentioned, due to natural discharges, magnetizing, pens and forks and knives. But this was a more laboratory observed experiment in which you would see the magnetic needle really be affected by a current carrying wire. Okay, so after Ørsted, as I mentioned, a number of scientists started to make mathematical formulation and measuring effects. Let's say put two wires together, trying to observe any attraction or repulsion between wires and so forth, how the effects varied with distance. So this set of experiments, we are not going to go through the details. There are so many different experiments, but I mean, we have after those experiments by Ampere, Biot, and Savart, you could establish the force law between current carrying loops. Just qualitatively here, before we introduce the final mathematical form, we have that the magnetic force, we have two, let's say, two current loops, okay, and we have two closed circuits in which we circulate currents, let's say I1 and I2. If we pick differential elements of each circuit, we could base it on the macroscopic force between the circuits. You could infer what would be the force between current elements. So you have here two current elements. I'm gonna define the L here and delta L there. Okay. So what we know is that the magnetic force, not the vector nature of that, the magnetic force, which is a force that has as its origins a circulating current. So between differential elements, is proportional to the product. I'm not going to put now the vector nature of it, just experimental evidence, which is very similar to Coulomb's law. Okay, Coulomb's law. It's proportional to the product of two elements of each of those circuits. I1 the L and I2 the L. Okay, delta L. So the force between those two elements, between differential elements, is proportional to the product of the I1 times the current length, the differential length of circuit 1, right? Times I2 current differential length of circuit 2. Also, let's say that the distance between those two, not like that. Let me just move this a little away so you could see here. Okay, so also, if you break the force down to a differential force between elements, let's call this a distance d. It's proportional to the square, to the inverse square of d. And that's it. The vector nature, well, vector nature comes from Oersted's experiment, you know. A current element, let's say if you have a straight wire, very long one, so this is going to produce an effect. So the effect of one circle on the other, each element produces an effect that goes with the right-hand rule. So the thumb is the wire direction. Your palm, your hand palm is the, you know, the direction of the magnetic field. So I'm not talking about that now. I'm going just to make the formulation more precise now. If you have now this geometry, let's consider that we have two circuits, C prime and C, location of current elements x prime and x. So we always put the, you know, the differential length, the differential displacement vector along in such a way that the path is always run so that the area is on the left. Okay, so this is the L prime, this is the L. So currents I1 and I2. So if we call F12 the force from circuit C prime over circuit C, so the total force, the integral effect of all the elements, and the dF12 is the force of circuit C prime on this element. Okay, and the differential of F12, the delta differential, which is associated with this element here, is the force from the L prime on the L. Okay. This second here. So what is observed experimentally is that the force of circuit 1 on the element dl, this element here, the total force of circuit can be written in this form: is the current on circuit 2 times dl times an effect due to circuit 1 that we call the flux density vector. Okay, magnetic field is some other concept that we are going to talk. It's very similar to the flux density vector, but this is not exactly the same. So the original field in the magnetostatics is the flux density vector, also called the magnetic induction. And so we see that the force has a cross product between the L and B. Okay, so the force is at 90 degrees with the direction of the L and at the direction of B1. What is B1? Well, B1, after several experiments and formulations, it was arrived at this expression. The field due to the elements delta L, which is this element here, delta L prime, is a constant that defines the unit system. This constant is called the magnetic permeability of vacuum. In this case, we have current loops in vacuum. So it's due to circuit 1, so we have I1 and delta L prime cross x minus x prime divided by this magnitude cube. So this is inverse square law, as I mentioned to you. And also, let's just let me just draw here the effect due to circuit 1. So it means like this: if we have a loop, you know, I1 that's dl prime. No, let's put it like this: dl prime. So the field at some point, this is x minus x prime, okay? So location of this one is x prime. Location of this one is x. So the field at this point here, delta B, delta B1, right? Is in the direction of delta L prime cross x minus x prime. If we make that, I mean, delta L prime times x dot cross product with x minus x prime, if the things are in the plane, it would be a vector entering, right? It's a vector here entering the plane of this screen, okay, of my screen, of my board, okay. So we have delta L prime cross x minus x prime, so it would be a vector like that. Delta prime looks like this. So that's the direction of the contribution of this differential element. So the effect on this point would be a vector like this. So it's like Ørsted demonstrated, right? Have a current like this is going to produce a B field like that in the hand palm. So it's like a cross product of this with the vector difference x minus x prime is going to be a vector like that. Exactly. Oh, so this cross product with that is the same as this right-hand rule. Okay. So that's the direction of the. So the effect due to the element, you know, delta L prime, is a vector that has this cross product. And again, we have the inverse square law built in this ratio here. The dimension is 1 over square of the distance. So the contribution of the differential element is delta B1, right? So the field due to this circuit as a whole is going to be the integral over the loop of circuit 1. Let's look at dimensions here. So if you go here at the definition, you see every time a field is defined as something related to the force. So that's the original formula. Force on a small differential element of a circuit due to a field that is in the you know, is around, is simply the product of the current element IDL times the field. So in here we see the dimension of B, okay? Dimension of B, the dimension of B is dimension of force divided by current divided by length. So we go here, we see the dimensional analysis. B field is equals to Newton divided by ampere meter. This defines the Tesla unit for units of B, which is Weber per square meter. Okay, so the field B has units in the international system of Tesla, which is Weber per square meter. Okay. Also, when we calculate the field, this formula here is what's called the Biot-Savart law, well known, that was derived after Oersted's experiments and other Ampere's experiments and other experiments by those two scientists. The parameter that appears in the formula, which is mu0, is called the magnetic permeability in vacuum. Okay, and the unit is 4 pi times 10 to the -7. This is the unit that comes out from the, if you use the force, the unit of B field, and all the other units, you obtain these results. So it's Weber per ampere meter. Weber per ampere is what is called Henry, which is the unit of inductance in the SE system. So we have permeability is a number, I have to record this number, very important to remember it, Henry per meter. So if we go here, so you have a circuit C1 and an element of circuit C2, okay? This is, we call delta L prime, right? And this one we call the DL. So you have two currents. So just see here, yeah. We put this in the next paper, next page. So the force is like this, right? The force on dF12. We have here like this, x and x prime, right? Equals to I2 dl cross B1, and B1, as we mentioned, equals to integral over the first circuit so the field due to circuit 1 on the position x of circuit 2. So it's cross product with x minus x prime over 4 pi x minus x prime cubed. So the total force F12 equals to the integral over circuit 2 of dF12. So the integral of this, so we put this here, and we obtain the force F12, the total force between circuits, equals to double integral. So so we're going to have something like this, like this. Yeah. I'm going to put like that. So it gets very complicated, but I mean, if we break down, I'm missing a mu0 here, right? Mu. mu 0. So that's what it is. And as I told you before, if you look at the expression, right? Here is the force. I just showed how to arrive at this one. Just showing that the differential, the force between differential elements is proportional to, as I mentioned before, the strength of the effect is due to I times dl, right? So it's IDL of one circuit times IDL of the other circuit, and inversely proportional to the square of the distance. And the magnetic force obeys the principle of superposition. Also, if you look at the force, we have to show this. I mean, we have a very complicated relation here, right? I can use the triple product here to show that the force can be written, you know, this is a triple product. Let's work a little bit more on this. So we have a vector identity A cross B cross C equals to AC B minus AB C. We're going to use this identity in this scene here to see what it is, equals to DL dot product with, this is A, right? A, B, and C. So the L times dot product with X minus X prime times delta L prime minus AB, which is DL delta L prime X minus X prime vector, right? So in fact we're going to have two integrals. I'm going to look at this one here. So if we let's just consider this integral here, okay? We're going to have something like this. Integral on C1, I'm going to put like this, the L prime first, then on C2, then we have, well, I'm going to put all the constants before here, mu 0, I1, I2 over 4 pi, okay? Then I have the second integral on C2. Then we're going to have this term here. So it's going to be the L okay, that's what we get. But notice that this, I think there's some, let me see here, oh, this delta L prime here. Okay, sorry about that. So that's one integral that depends on that one. But this one, I mean, you see that this one is the gradient of the inverse function, right? Unless of a sign. In fact, this is minus gradient of 1 over the magnitude vector of the difference. So, and we know that the circulation of a field that is obtained through the gradient of a scalar function is always 0. So this thing here is 0. So the contribution of this term here to the integral is 0. So you only have this one, right? Yeah, I think it's correct. So, so you obtain, when we plug, I mean, have a minus sign here, then we're going to plug there. So we are going to obtain F12 equals to minus, as we have in our notes, right? C1, C2, mu0, I1, I2, vector x minus x prime. The vector nature is right here. Yeah, it's correct. The L delta L prime divided by 4 pi So you see that we see the nature of the force. The force is along the direction that separates the two current elements. The two current elements have the line that separates the two current elements. The force is parallel to x minus x prime. Let's see if that's correct, huh? Let's take a look here. So I have this current element here and this one. So the force that this current element exerts on this point is, if they are like this, it would be something like this, right? So let's see if that's correct. That's the force F12. Would be attractive like this, right? So I have a minus sign. Well, what is the field due to I1? I'm going to draw just the direction of the field. The first field due to I1 is something that enters the screen, something like this. And the force on this element here is I times this vector, right? This vector cross product with this vector B, which is entry. So this vector cross product with that is going to be a force like this. So the force between current elements is aligned along the direction that separates the two elements, just like Coulomb's law, right? The only difference is that the elements that produce the force are vectors, because it's current times current displacement vector. So this product is the element that produces the effect. Those are the elements that interact. So the force is along the direction between the two, after we do all this math, we obtain these results that shows that the force is along, have a minus sign there, along the direction of x minus x prime. And then we can notice that the force obeys the principle of action and reaction, Newton's, right? If we interchange the elements, this is unaffected, this also. We just change this one. This is unaffected, so we obtain that would be plus here, okay? So if I change the position here, I'm going to have a plus. So it's going to be minus F12. So please correct the class notes on that sign. So the magnetic force, in summary, right? The magnetic force, as I mentioned before, is the IDL cross B famous formula. And B is the fundamental field quantity. Everything else is going to be defined as quantities. B is the quantity that gives the magnetic force. And B is called the magnetic induction vector, or the magnetic flux density. Magnetic flux density vector. So to determine F, we have to map the vector field of a number of, current distributions. We have to look at, for instance, currents that are in volumes or in surfaces. What are the formulas? So we have to get used to determine B field of certain distributions. So that's the scope of magnetostatics in this initial part, right? So let's do some examples and get used to the behavior fields of certain current distributions. Let's look at this situation here, in which you have, in fact, you have any circuit of any shape. If you look very close to the circuit element, what would be the magnetic effect? That's a fundamental question, right? How does it vary with distance from the, if we expand this, I want to look at the, can go a little farther. So I have, at this point here, I have certain distance, right? So at this point, we are very close to the circuit, as you can see, right? So if you go keep expanding, magnifying it, we're going to have a straight wire, right? So how is the field, how does it depend on the distance, on the currents that circulates on the loop, on the circuit, and so on, right? For instance, when you walk below a high voltage transmission line, what's the magnetic field on you? That's an interesting question, right? So we can try to answer that by making a very simple model, assuming that we have, a straight wire. And we want to determine the field at a certain point. Straight wire that is as large as possible. Let's assume, for simplicity, that is infinitely long, so we have some, we take some advantage of symmetry, translation symmetry, right? So we can calculate the field at any point, at any plane that cuts the, because if the wire is infinite, you can cut it in half everywhere, right? So let's do that. So here's the geometry. I have this wire. So you define a coordinate system. The origin is in the middle of the wire. So I have a distance. This is mostly a cylindrical system, right? Let's try cylindrical. I have an azimuthal angle phi and a distance r. We have a current I. So the differential length on the circuit is a wire, in fact, is dz prime. Location x prime is z prime az. If you look at the formula for the field of a current loop, it's a Biot-Savart's law. We're going to drop the index. Now it's going to be something like this: B equals to integral of this is the formula for the field of a loop, okay? That's Biot-Savart's law. So what we have to identify to calculate the field, we have to identify what is x, what is x prime, and how to represent the L prime. So I have to define a coordinate system. Due to the nature of the field, which is solenoidal, it's reasonable to assume that it's better to use a cylindrical coordinate system. Right? So if you look at the geometry, let's find these elements. We have x is right here. So if you look, x is equals to r times ar. Right? X prime is right there. z prime az. So recall that in our notation, every time we have a prime variable, that's the one that's being integrated. Sometimes we don't do that, but when we need to avoid ambiguity, we do that. Okay. So on the L prime is the element that has a component dz prime along the z direction, so it's going to be dz prime az. Notice that this is not a prime, so ar is a constant vector. Okay, it's standing there. I'm scanning on the current distribution, but I'm observing the integral of all effects along this vector here. So let's try to do that, to do the calculation. So we have b equals mu0 over 4 pi I. I'm just removing everything from the integral. The integral on a closed loop is like a minus infinity to infinity. The dl prime, which is the form, is dz prime az cross x, which is the location ar, minus x prime, which is z prime az, divided by magnitude of rar minus z prime az. So everything that's prime is variable here. Everything that doesn't have a prime is constant. So these are orthogonal vectors. This is r squared plus z prime squared to 1/2 to the third power, so it's going to be 3/2, right? The cross product between az and az is 0, so we have az with ar. Az cross ar is a phi. So b equals, and I'm going to, well, do like this. dz prime, so az cross ar equals a phi times r, right? Times r a phi. This one was 0 az with az 0, so we have this denominator here. And the B field, well, we can remove things that are constant. Those two elements, they are constant. They are located at the position of the observation point. R is fixed. A phi is a constant vector. I'm not varying the azimuthal coordinates, so it's constant. So this is going to be, you know, so we have an integral which I leave for you to do. This is an easy one, okay? I'm gonna make it. If we make a change of variable, the traditional one, z prime equals r. Let's make r tangent of an angle, okay? So as z prime goes to infinity, the angle goes to pi over 2, and z prime goes to minus infinity, the angle goes to minus pi over 2. So what else we have here? Z prime square plus r square equals to r square 1 plus tangent square. Let's use the English, right? The English notation, which are tangents of alpha, which is r square secant square of alpha. And also dz prime equals r derivative of tangent secant square okay, so what we have here is that the integral is like this. Dz prime is here, so it's going to be integral from minus pi over 2 to pi over 2 r secant square alpha d alpha divided by r3, so it's r squared times 3/2, so we have r3, and secant square to the 3/2. Well, secant between minus pi over 2 to pi over 2 is always positive, so I can extract the positive roots, no problem. So secant square to the 3/2 is secant to the 3rd power. So that gives me 1 over r2 integral of the cosine. Well, integral of the 1 over secant is cosine of alpha d alpha. And this is going to give me, if you calculate, it's going to be 2, okay? It's going to be sine, right? 1 minus 1 equals 2. So the result is 2 over r squared. If you look back here, this thing is 2 over r squared. So I have the field, which is this result here. This result is the field due to a straight wire, goes with the inverse of the distance. If you look at the field lines, it would be something like this, right? I mean, azimuthal direction. So the field would align, like this. So that's why if you put a compass here, the needle is going to align along the direction of B, naturally. That's what Ørsted observed, right? With a compass like this, the needle is going to align at 90 degrees with this wire, direction of the wire, right? And also the force that Ampere made several experiments with force between straight wires or between a circuit with very long parallel wires, have a closed loop, like this, or not, right? You can have a circuit like this and another like that, and you can look at the behavior of the wires as you, if they are reflected when you circulate the current or if they are repelled. Can make us, a closed loop like this. Then you have a current that goes like this. And you can see when you turn the circuit on, if the thing, if you have attraction or repulsion. So if you look at the force between two circuit elements, let's make like this situation here. Have two, parallel straight wires. Let's locate one on the z-axis. Let's put the other one at a distance d along the y-axis, like this. So let's see what happens when you have two circulating currents. Well, we know the field due to B1, right? So the force on an element, let's call it dz. So the force, dF12, equals to, according to our experimental law, is I2 dzaz cross B1, which we already calculated, which is mu0 I1 divided by 2 pi. R in this case is the distance d times a phi, but a phi at this, So that's the direction of the field, which is along the minus x direction, right? So we would have here minus ax. So we have az with minus az with ax is ay. So az, the vector direction here is going to be minus ay. So we're going to have the product I1, I2, dz, and the distance d. So you can calculate then the force per unit length between two parallel wires. It's going to be this formula here. And that's what Ampere measured, this type of effect here. So the force is the product of the currents divided by the distance, and the direction is orthogonal. Sorry, it's along the the line that separates the two wires at 90 degrees of the wires. So it's going to be minus ay, as we already told you before. So you see that if the wires have currents that go along the same direction, you're going to have an attractive force. So you have a circuit that has currents going in the same direction, they're going to be attracted, right? And you have currents on opposite directions, they're going to repel each other. So that's what we have, okay? Let's move on. Let's do some additional examples. Let's get used to the magnetic effect. Let's have we have a circular current loop. Let's use this geometry here, this construction. Have a loop, a closed loop with a current equals to I. Right? So let's calculate now. We are going to have to, we have to calculate everywhere the magnetic effect, but let's do that after we talk about the vector potential, which is going to help us to do that. For now, we're going only to calculate the field on along the z-axis. So x is z, x prime is a location on the loop. Now is a variable, ar prime. Okay, we have this dl prime here. So is the length on the circumference differential length is a d phi prime, a phi prime. Sorry, d phi prime, a phi prime. Right. So let's use the Biot-Savart law. Let's calculate it. B equals to mu 0 I over 4 pi, which is always outside of the integral. So closed integral, the variable is going to be the smoother variable is going to be, we can write like this already, right? So the dl prime is a d phi prime, a phi prime, cross x is the z-axis. We want to see the effect on the z-axis. This is the locate. This is wrong. Sorry about that. Location x prime here equals to x prime equals to a, which is the magnitude, times ar prime, which is a variable vector on the loop. So then those vectors, those versors are orthogonal. So the magnitude cubed is going to be z squared plus a squared to the 3/2. Right? So we have the field. Notice that this is constant. I can put it outside of the integral. So the A comes out. So I have the cross product here. Let's put the d phi prime here. A phi prime with AZ, the second and third vectors on the basis for the cylindrical system is going to be AR prime. Okay, Z AR prime. That's this cross product here. So this other one, A phi prime with AR prime, the second and the first is minus the third. With this minus, it's going to be plus. So it's going to be plus A, AZ. So that's what we have. So I have two integrals. Right like this. So I have two integrals. One which is this goes outside of the integral, Z plus A. Well, here AZ also is constant, so AAZ so this is 2 pi, right? Well, this integral here, remember that this is summing AR prime for different phi's on a closed loop. It's going to give 0. You recall that this has two components. One is cosine phi, the other is sine phi. Cosine phi AX, sine phi AY. Both integrals are 0, right? So the integral for AR prime is 0. If also, if you want to do it, in an elegant way, you have that dA phi, d phi equals to minus AR prime. So AR prime equals to minus dA phi. Yeah. D phi. So the integral of AR prime equals to minus integral of which equals to the indefinite integral. So between 0 and 2 pi equals to A phi between 0 and 2 pi, which is the same vector, right? A phi prime at 0 and at 2 pi they are the same, so this is equals to 0. So this term here is 0. So we only have that one, so we're going to have a square of A here, right? And have a direction AZ. And then we have the result shown in this screen. Okay? That's the result we have. The B field of a current carrying loop on the z-axis along the z direction. We are going to show you that the magnets, right? The magnets, let's make a whole bar, okay? Cylindrical magnets, magnetized, is like several current carrying loops in parallel like this. So each one in the center produces a field like this. So a magnet would produce an effect like that. Of course, the thing is going to do, closed configuration like this. I'm going to show how to do it, but the basis is this expression here. The field due to a single loop is along the z direction, is maximum at z equals 0, right? So B at z equals 0 is going to be, we have yeah, I forgot to tell you about the other integral, right? I was talking about the zero integral, but this one, yeah, this one, the 2 pi is there, right? Yeah, that's why you don't have a pi in the denominator, right? So at z equals 0, you're going to have a squared divided by a to the 3rd power over 2a, az. That's the field in the middle, you know, right at this point here. Okay. Let's generalize now the force formula. Notice that the element that contributes to the force, if you have an element, the force, right? The force on a current element, dF, I have a field, right? If we're not talking about the force, right, or the Biot-Savart law, you can talk about the field and have a differential current element. Then you have the differential force, right? So every time, the important element is the product IDL. That's what appears here. That's what appears in Biot-Savart's law. So it's important to generalize the concept. I mean, here we have a current that's on a single wire. If I have a current volume on a volume, how would we change the formulation? Let's say that we have a volume here, right? That's area, length dl. So if you count the element that is in all the formulas is IDL, let's remove the vector nature for a moment. So I equals to J times the area, let's say sigma. So is J sigma is equals to I times dl. So sigma dl is dV. So what we have to do is to replace IDL by J dV. And the vector nature, when we talk about wires, we put the vector on the wire direction, right? When we have, if we change that to current density, the vector nature goes not to the volume, but to the current density itself. So the change that we have to make in all formulas is IDL equals to J dV. Also, if you have a surface instead of a volume, have a two-dimensional region mostly. So we have a current that crosses a length W, transverse length W, and a thickness D. Okay. The surface area is the sigma, so we would have a current surface current density. So let's relate IDL, I times dl, with the surface current. What happens? IDL equals to J times the area here, this area here, is D, right, times W. So J times dW is the current, dl is the length. So then you can, JD, in the limit that D goes to 0, becomes the current surface current density, and WDL is the surface area, right? WDL is the surface area here. So it's the same as making IDL equals to K the sigma, and we put the vector nature on the current density here. So for surface currents, we make the replacement IDL replaced by k d sigma. Instead of line integral, we have a surface integral. If you go to the volume, instead of a line integral, you go to a volume integral. So you can generalize all the formulas. Okay. So in summary, that's what we have. Right? If we have surface currents, IDL is replaced by k d sigma. That's the geometric construction area. K is on the area. Volume currents, IDL is replaced by JdV. Then you have this tube piece of volume like this. So we can calculate force on a surface, force on a volume, right? If we have a current sheet with current density K, area d sigma, we can calculate the force on the area d sigma using that correspondence. This is the same as IDL, right? We replace it by k d sigma. So the force is going to be integral on the sheet surface, like this one. On a volume, we have a volume of current subjected to a B field. So we have again IDL replaced by JdV. So we're going to have this change. Now the integral is on the current distribution. Is going to be this result here. But let's make an example. So let's calculate the force on a point charge moving with velocity v. I'm just looking at my notes here. I think there's some misunderstanding here. I think I should make this. I'm going to make the right notation. So let's say that we have a point charge Q located at the point X. Okay, it's not X prime, it's X. Located at the point X. Right? And at a given point X prime, we have, so we'd have something like this. We have the current density of point charge Q moving with a velocity v is rho v. The density, if the location of the charge is x, would be, so let me fix here. So it's going to be x prime is a variable vector, okay? So it's going to be x prime. I'm going to put in red so you can fix there. Minus x, okay? So that's the delta function that determines the location of the charge on point X. So the current density would be x prime minus x. This is a function j of x prime. X is fixed. So, so you have a b at a variable point x prime. So the force on the particle would be the integral of dv prime jx prime cross bx prime. Okay. So this is, I have to fix here. So this is going to be integral of delta of x prime minus x times bx prime. That's the right way to do it. Okay. So just revising, so the current density rho v, rho is a function of a variable x prime, x is fixed, is the location of the particle, so the current density is this formula here. So we integrate a delta function and it's going to pick up the B field at position x. So the result we obtain is that the force on a single point charge moving with velocity v is the famous formula QV cross B, right? So if you have a velocity like this and a field that is at 90 degrees, the force is going to be, you know, V cross B like this. So the tendency is to deflect the particle in a trajectory that's curved relative to the original direction. So the velocity is always tangent to the trajectory in this case. Okay? So please fix those x prime x in your class notes. I will try to remember to do that in mind. So let's do that. Let's make the generalization of Biot-Savart law for currents, for a surface current, and also for a volume current. As I mentioned, IDL now becomes K d sigma. So here you have, I don't know why this thing is like this blob, this white blob here. Let me just remove this thing here. Don't know what this is. Something that's in the drawing. Let me fix it here. So, so that's the sigma prime is this element here. K is the surface current density. This surface sigma instead. This is sigma. Sigma, not S. Right? So, so all we have to do is to replace IDL by K d sigma and make it an integral over the surface. So we always have IDL K d sigma here, same formula, no change, okay? Also, if I have a volume of current, all we have to do is to replace IDL by JdV, and now we have an integral that goes on the volume like this. That's the generalization of Biot-Savart's law for a current distribution. Let's make another example. Now we have, let's make an example of a surface current. That's another important idealized current distribution that we can calculate the field, right? Suppose I have a uniform, distribution of current on a surface. We can calculate the field. If this is very large, the surface is very large, infinitely large, you can calculate. I mean, you can calculate for a finite surface, but let's make it for a, infinite surface. So we have some symmetry here. Without laws of generality, we can calculate the field on the z-axis, can place the origin anywhere in the plane because the plane is infinite. So here we have, we can calculate, we can break, for instance, I can break I can calculate in several ways. One of them, I can assume that the plane is a set of parallel wires and use the field of a parallel wire, of a straight wire to calculate the field of that wire and sum. But you can calculate in a different, using the formula, and that's how I'm going to do it. I'm going to use the formula. The B field, I'm just putting the constants outside. The surface integral over the surface of the z equals 0 surface. So it's going to be K, I'm going to put the formula here, the sigma prime cross x minus x prime divided by x minus x prime cubed. Instead of considering a plane, I'm going to consider a disk. infinite disk. Sorry. Let's make a piece of the disk like this. I'm just putting here, you know, X, Y, and Z. And I have a surface element here on the disk, this sigma prime. So I'm going to start using cylindrical coordinates to determine the field at this point, ZAZ. Here we have R prime, AR prime. So X prime equals to R prime, AR prime, and X equals to ZAZ. And the surface element is equals to that in cylindrical coordinates is the arc times this shift here is R prime, D phi prime, dr prime. So, and K, well, K is a constant, is a vector like this. It's K0 AX in our construction, right? Let's move the drawing here. That's K. It's a vector that is constant along the X direction. Okay? So when we plug that in here, we're going to have, let me bring this down here. Put here. I'm going to keep replacing it. So let's put K0 here. K0 is out, AX. The sigma prime equals to R prime, dr prime, d phi prime. X minus X prime equals to, we have here, right? Z minus ZZ minus R prime, AR prime. And here in the denominator, we're going to have instead those orthogonal vectors R prime square plus Z square, 2 1/2 to 3rd power 3/2. Okay. Now, we have, let me just remove this in here. So the B field AX, well, I have to make cross products here. AX with AZ and AX with AR prime. So one contribution is AX with AZ. First and third gives minus the second. So we're going to have one contribution which is minus AY. Okay. Then we have double integral. Integral in R prime, all the disk is an infinite radius, so R prime, dr prime. Then the contribution is this one, right? AX cross AZ gave this one. So we're going to have a Z, which can be placed outside of the integral, the Z here. So it's going to have R square plus Z square to 3/2. The other integral is going to involve the cross product of AX with AR prime. So let's see, just here somewhere, here, AX cross AR prime, right? So we have AX, AR prime, they have an angle phi. So it's going to be sine of the angle, sine of phi, in fact is prime here, times the vector that is orthogonal to both, which is AZ. So you're going to have an integral involving sine phi, which is going to give a 0 result. So the second term doesn't contribute to the integral because it involves integral of sine from 0 to 2 pi, which is 0, right? So that's all we have. It's only this term here. So this doesn't depend on phi, so we're going to have a 2 pi here. And this integral is very easy to calculate, right? So when we do the calculation, we obtain, we see that 2 pi is going to cancel the 4 pi, right? We're going to have a 2, then we're going to have a minus, and the AY. That's the result we get, okay? So that's what we have. I mean, it depends, in fact. Because here we have an integral that has a root square. When you calculate the integral here, this integral here, is going to give a function that is equal to r squared plus z squared to minus 1/2. So we have to make sure, from r equals 0 to infinity. So at the end, they're going to have something like z squared to minus 1/2. So we're going to have to use the magnitude, in fact. Okay. So this result is a result for z larger than 0. The correct result, I'll leave to you to show it. It's going to be something like this. So we have a magnitude that arises because of the integral, which involves the square root of z squared, and the square root of z squared is magnitude of z. Okay? That's why I have this ratio here, which is constant, in fact, right? It's constant, but it's +1 for above, this is positive for z larger than 0, and this is negative for z less than 0. So the field is always, I mean, it's an idealized current distribution, which gives a constant field everywhere, even at infinity. So I have a field that goes to the left above the plane and goes to the right below the plane. It's like we have several straight wires packed up together like this. We would have an effect, due to several of those. If you sum those, you're going to have something like this and something like that. That's what we obtain. Okay? Well, we have made some examples of magnetic induction field for several distributions, or magnetic flux density for several distributions. Well, let's now find a potential quantity for this vector, like we found the potential quantity for the E field, the scalar potential. Now we have a vector potential, which is called the magnetic vector potential. So let's go back to the original Biot-Savart formula, a generalized formula for a volume current, right? Let's use that well-known quantity, x minus x prime equals 2 divided by the magnitude cube, because minus the gradient of the inverse function. So recall that we have an identity that the curl of a vector times a function equals minus the vector. Let's write separately here. That's the identity we use for that one. The curl of a vector times a function equals minus vector cross product with the gradient of the function plus function curl of the vector. There's one chain rule that we have. We use f for the inverse function. And for a, we use j. Right? Recall that in the integral here, j is a function of x prime. Right? I have two elements. X is the observation point. X prime is the location of the volume element variable. So we use that first identity. So we have the chain rule. Curl of a vector times a function, which is the inverse function, equals to, if we move this to the other side, right? Equals to curl of the vector times the function minus vector cross product with the gradient of the function. Now, notice that the nabla vector here is relative to the x variable, not x prime. Okay? So we have derivatives like this. So nabla makes derivatives relative to the x location, not x prime. So because j depends on x prime, the curl of j equals to 0, because this doesn't depend on x. So this term is off, right? So we have that the cross product of j with the inverse function, which is minus nabla, equals to the curl of j over x minus x prime. So you have something like this. B so we change that to B equals to curl of j of x prime divided by x minus x prime. Well, I can simply apply this is operating on coordinates of x. The variable of integration is x prime, so I can put this operation outside of the integral. So I have b equals to the curl of an integral right? So that's our potential function right there within brackets. So we show that b can be obtained from the curl of a vector. We call it the vector A. So vector A is called the potential, the magnetic potential vector, which is a simple integral. It's very similar to the scalar potential, but the only difference is that there in the scalar potential we have a charge density. Here we have a current density, which is a vector. There is a scalar. That's the difference. So it means that if I calculate vector A, I obtain B by doing the curl of A. Okay? Also, the dimension of the potential vector doesn't have a physical meaning as the scalar potential in electrostatics. So this has a dimension of Weber per meter. Well, if you want to use Tesla, Weber per square meter is Tesla, right? Equals Tesla times meter. Okay, the same thing. So that's the formula. Notice that the vector nature of the formula is much simpler. A and you have a J here. There's no cross product, simple term here. This means that if you look at the relationship between the contribution of a single volume, differential volume, dV prime, the contribution of this volume, let's say that the current is aligned in this direction here, the contribution of this volume is going to be a differential potential vector, which is in the same direction as J. So, I mean, if I have this other element here, let's put another element here, has a current like this, J1, well, it's going to give a contribution here, dA1. So the result here is the sum of all the contributions, but each element contributes to the collinear differential potential vector. For instance, if we have a straight wire, if the current is always in the same direction, well, the potential vector, the vector potential, in fact, is always on the same direction of the current direction here. So everywhere the vector potential is going to be along the same direction of the distribution. If we have a current loop like this, well, we are going to obtain similar potential vector potential that resembles the current loop configuration. Okay. Well, we have some special formulas for the potential vector if we have, special cases. If we have a surface current or a wire current. Okay, just as always, right? J dV becomes K d sigma. So that's what we get. A equals 2 K d sigma. So this is wrong. This is wrong. There's no x prime here. There's no cubed. Notice that we have an inverse law here. Okay. So we have that. So that's the formula, right? So please fix that in the class notes. So the inverse of the distance that appears, the magnitude is a simple magnitude here, right? It's not the third power. There's no cross product. Well, if we move to current loop or current wire, seeing one-dimensional distribution like this, it's going to be this change. And we have the formula for the potential vector. In this case, have a closed loop, right? Because this is a stationary regime in which the current always makes closed loops. Okay. So we are going to explore a little more of those things in the next lecture, but we are going to end this class today by doing the formulation Maxwell's equations for vacuum magnetostatics. Now that we have a potential being introduced in the problem, we have one equation. If B is the curl of A, we know that B is going to be a solenoidal field, because every field that's derived from the curl of A is solenoidal, like this. So the divergence of B equals 0 means that there is no, no magnetic charge, because if there were magnetic charge, we would have something not zero on the right side. So the magnetic induction, or the flux density, magnetic flux density, is always forms closed lines in space. There's no beginning, no end, so there's no point charges magnetic point charges for the B field. First conclusion, that's the first Maxwell's equation in magnetostatics in differential form, and which will be valid also for dynamic fields. Okay, that's going to be one of the Maxwell's equations. We need a second relation. We need the curl of B to determine B completely. You have to determine the curl of B. So let's calculate it. What is curl of B? Well, let's use A as our vector. So this is going to be identity, right? Curl of A equals to gradient of the divergent of A minus the Laplacian of A. Laplacian of A, right? So we have to know, well, what is divergent of A? We know the curl of A. Curl of A is known, equals to B. What is divergent of A? Well, whatever I do with divergent of A, I don't affect B. Okay, but let's calculate it anyway, the way A was calculated. Let me, before I go on, let me just recall to you that we said that A has a formula, right? Sorry. Mu 0 4 pi x minus x prime. We said that because we showed that B equals to curl of this integral here. Because of that, right? Well, notice that I can add something here that has a zero curl, like a gradient of a function, without affecting B, okay? So I can define different vector potentials, well, without affecting B. We are going to talk about that further. I mean, it's the choice of a gauge for the potential. A gauge, it means a choice of, if you use, sometimes we might want to use an additional term, sometimes it's not convenient to use. We're going to talk about that. So I just want to let you know that we have a freedom of choice. I can always add a term that has zero curl without affecting B, right? So, but let's use our formula for the A like this one. And let's calculate divergent of A. So here we have the nabla goes directly into this inside of the integral because in fact here we have recalled this dv prime, right? So the integral is on x prime, so the derivative is relative to x. So I can enter with the nabla inside of the integral. So if we calculate again a chain rule, divergence of a vector times a function, well, it's going to be the vector times the gradient of the function plus the function times divergence of the vector. But divergence of the vector is 0 because the vector here in this case depends on x prime. Okay? So it means divergence of this combination is given by this formula. If I change nabla to nabla prime, right, I would have an additional term that would be the divergent prime of J. But this one is 0 because we have stationary currents. For stationary currents, the divergence of the vector is 0. So in other words, if I use the prime variable, I have this result here. And then we know that nabla prime has, the only difference between them is a sign. Okay? So it means that the divergence of this is minus the this is the property. The gradient of the inverse function relative to one of the variables is minus the gradient relative to the other variable. So it means that the divergence of J is minus this divergence here. Let's call this the result A, okay? So, so it means that I can simply put a minus here and put a nabla prime there. That's what it means in practice. All of this is to show that I can put a minus sign there and put a nabla prime instead, right? So that's what we get. So here we use Gauss's theorem. Integral of the volume of the divergence of a vector is the flux of the vector, which requires the normal component of the vector on the surface divided by x minus x prime. So this is the vector. So you have a localized, right? I mean, we have to enclose the current on the volume. Outside, J equals 0. Inside, J different than 0. So what is the normal component of J? Well, we showed that J normal is, J normal 2 equals to J normal 1 for a stationary current distribution. We showed that in previous lecture. But outside the current is 0, so this is going to be equals to 0. So the normal component is always 0, because outside there is no current, and the normal component has to be conserved, so outside is 0. So the integral is going to be 0. So in this gauge, particular gauge for this potential function, in which is just the integral, right? The divergence of A equals 0. Okay? So then we have curl of B equals to, this term 0 is minus Laplacian of A, and let's now move on to calculate Laplacian of A. So to calculate curl of B, I have to know Laplacian of A. So if we break A in rectangular coordinates, it's easy to calculate the Laplacian, because the versors are constant. Laplacian goes directly to the components, right? Well, if the ith component is given by this expression, we, want to determine Laplacian of AI. Let's recall that for the potential function, when it is given by this expression, Laplacian of the potential function is given by this relationship here, right? So similarly, if I have, if I make a correspondence, I replace phi here by AI, rho we replace by ji, and epsilon 0, which is in the denominator, we replace by 1 over mu 0. Right, that's the correspondence we make. Rho goes to Ji, epsilon 0 goes to 1 over mu 0, and phi goes to AI. So I calculate like this, the Laplacian of AI equals to minus mu 0 Ji. Now, when I recompose here, this is going to be equals to minus mu 0, sum of AI Ji, which is equals to the vector J. So that's what Laplacian is. It's minus mu 0 times J. Okay? So summarizing, right? We have this. Laplacian of AI is minus mu 0 times Ji. If we compose sum all the components, we're going to have the final result. Laplacian of A equals minus mu 0 J, which is what we needed to obtain curl of B. So curl of B equals to mu0 times J. That's the second differential equation we needed to determine magnetostatics. We have two equations now, two Maxwell's equations, differential form for magnetostatics. We have the field is solenoidal, and curl of B equals to mu0 times J. Okay? Well, we are going to introduce the magnetic field in vacuum. Magnetic field is another quantity. It's not the magnetic induction field. It's not the magnetic flux density field. It's the magnetic field. In vacuum, we're going to have a more generalized connection between fields. But now, in vacuum, we're going to define H. The idea is to eliminate the mu0 from this equation here. So we're going to put B equals to mu0 times H. With this definition, if you look at the, at the dimensions, H has a dimension amperes per meter. If we put this here, we have the second equation becomes curl of H equals to J. Okay. So for now, we introduce the magnetic field measured in amperes per meter, so that we simplify the second equation. Go to curl of H equals to J. So we have Maxwell's equation for vacuum magnetostatics. Okay. So we have two equations and a connection between fields. One field is the magnetic induction, or the magnetic flux density field, and the magnetic field. So curl of H equals J, divergence of B equals 0, and B is connected to A in vacuum by this relationship, which will be more general when we talk about magnetic magnetostatics in material media, right? So if we apply our well-known integral theorems, we obtain integral relations. Well, one is from, from the divergence of field equals 0 means that the flux outside, the next flux outwards or inwards of a closed surface is always 0. There's no magnetic charge involved. And the other one is Stokes' theorems yields this relationship. The circulation of H is not 0, but equals to the total current that is enclosed by the loop. So the loop C encloses the area sigma. Okay. We are going to the next lecture explore a little further this concept. So just to give you an idea, this is called the amperes circuital law. The name was given by Maxwell, in fact. Maxwell Maxwell derived some of those things and decided to make a tribute to Ampere, giving the name of Ampere to this law, to this integral law, for the case of stationary currents. So let's just take a look at the scenarios that we have for the application of Ampere's law. We have here a cylinder having current that is distributed across the cross section. You know, I can enclose several regions of this cylinder. I can enclose the whole cylinder with a closed loop, part of it, right? Or I can just make a loop outside of the cylinder. Okay. If I enclose the cylinder with an external loop like this, so the integral, the area that's enclosed is this area here, right? So in fact, this is H. We are using H. Okay. Oh, it's right there. So when we make the integral over the area, over this area here, outside of the cylinder, the contribution of the integral outside, let me make a little better here, make a little smaller, the contribution of the integral in the area that's outside of the cylinder, right, this area here. So this contribution here is going to be zero. So in practice, when you make a loop that is larger than the cross section of the cylinder, the only thing that remains is the part that is the net result is this part here. Let me use this color here. That's, I mean, in practice, that's the integral we're going to calculate along the cross section of the cylinder. So the integral over C3, right, is going to be the current, the total integral of J on the cross section is going to be equals to I. If you make a loop that is, you know, partly picks parts of the cylinder, in practice, the only part of the integral that's going to be not zero is going to be this one in this intersection area here. So the remaining integral is going to be zero. So this region here in green is going to give zero contribution. So when you make an integral over C2, in practice, the result is the integral on this this area here, which is smaller, gonna give a result. Oops, it's gonna disappear here. Oh, here. So in practice, the result is gonna be a value that is less than I, smaller than I, right? And if now if you pick the integral, if you pick a loop that's outside, right? If it doesn't enclose anything, you integrate. That's the area that is enclosed by the loop, but across this area there's no current, so the result is going to be zero. So we have to be very careful when applying Ampere's circuit law. We have to always understand that the loop, the area is the total area enclosed by the loop, and the integral across the area in practice is going to occur only in regions where the current is not zero. Okay? So we are going to conclude this lecture at this point, and we will continue next lecture on the magnetostatics subject. I hope to see you next time. Bye-bye.